Good day, class. This is Moe Shahram, and this course is Physical Science Survey at West Valley College. And today we are going to talk about the concept of light, cover some of the properties of light in terms of its wave and particle behavior. Before we do that, we talk about a little bit evolution of theory of light, and then we look at wave and ray aspect of the light, where ray aspect means that you have a stream of particles that are traveling in a straight line. And then we're going to look at some of the properties of light interacting with other objects, such as reflection, refraction, and then interference of light waves with each other. And then we talk a little bit about polarization and dispersion, and cover some optical devices such as lenses and the eye, the most important optical device that we know of. And then we see what happens when things start moving faster and faster and getting closer to the speed of light. We touch upon special relativity and general relativity. There would be a lot of video demonstration and animation in this chapter. For the longest time, our ancestors were debating between what is light and where it comes from and what is the nature of the light. Some, they thought that it's rays of particle coming from luminous bodies. And some thought that the light is a stream of particles coming from our eyes. This idea went back and forth until about 18th century, when Newton declared that light is a stream of particles. Now, at the same time, Huygens declared that light is a wave, but Newton, being a more popular scientist at the time, his idea was accepted until about 100 years after that, when Young conducted an experiment, shine a light onto double slit and show that there is an interference pattern due to the wave nature of the light. So that was the experiment to verify theory of light being a wave. Then it was until about 1862 that Maxwell came along and with his set of equations describing the light being as part of electromagnetic waves. Then at the beginning of 20th century, Einstein and Planck proposed that light can sometimes behave like a wave and sometimes behave like a particle. And light comes in a discrete amount of energy. And we discussed that in previous chapter. We talked about that light or electromagnetic wave emits from an accelerating charged particle. So if you manage to accelerate a charged particle in any manner, you would emit electromagnetic wave in space. That electromagnetic wave, as a result of the Faraday's law we talked about, waves are self-sustaining and oscillating and propagating in space. Of course, that oscillation has to be in right frequency, and at that right frequency the light is emitted, propagates at a speed that we know it's the highest speed that we know of, the 3×10⁸ meter per second. So that would be light emerging from oscillation of electrical charges. We talked about particle nature of light, as we called it, a photon, via photoelectric effect that was proposed by Einstein. Now we are going to look at how these photons, stream of photons moving in a straight line, can interact with other objects. All right, let's now talk about wave and ray nature of light. We know that all matter emit electromagnetic radiation, depending on temperature. When you have an object that is luminous, emits light, there's a lot of acceleration of charged particles within that object, which causes emission of all that light, such as a lamp, incandescent lamp, or the sun, or a flame. All of those are as a result of charged particles being accelerated. When bodies emit electromagnetic radiation, frequency would be different as part of dependence to a temperature of that object. The black body is defined as an ideal emitter or absorber of a light. That means that it can absorb and emit all the light perfectly, but of course we really don't have a black body. It's an ideal definition. The increase of temperature causes that the amount of radiation to increase, because you are now exciting the charged particle more and more, so therefore there would be more radiation. So as you can see, at the lower temperature you have less intensity. As you increase the temperature, the intensity increases. At the same time, the peak of intensity moves towards higher and higher frequency. Moving to the left is higher and higher frequency, a shorter wavelength. Now, a lot of objects around us are emitting radiation. We don't see it, but if you have an infrared camera, you can actually see that. And they're kind of at a very low intensity that it doesn't even appear in this graph. The red one is around 3000 Kelvin. That's still very hot. Normal things around us is about 300 Kelvin. When the light interacts with some objects, depending on the nature of the object, how smooth or how rough that is, it reflects from it. And it also depends on the nature of that material, the color of that material, how the light is incident upon that material. In the process, the light can be absorbed by the object or can go through the object if it is a transparent material such as glass or plastic or air. Or it can be reflected from, bounce back from that object, or it can actually penetrate into that other object or media, and its speed can change and it can bend, and that's called refraction. So let's look at some of these phenomena. Here we have a representation of a light in terms of a wave. Obviously we show that with the sinusoidal wave here. And then when we look at it from top, we can just show it with a series of parallel lines indicating the wave crest or maximum or plane wave propagation in that direction. When you have a group of photons that are emitted from a source, then you have a straight beam of light. So we can treat that as a ray of a light. Okay, so let's look at the reflection. When the light is hitting a surface of an object, it can bounce back, and depending on the angle, depending on the type of surface, it can bounce in a different manner. If you have a very smooth, shiny surface, it can bounce back with the same angle as incident on that surface. Look at a light that is hitting that surface with a certain angle, let's say theta I, and it reflects back with theta r, which is the angle of reflection. However, when we show the ray of the light, keep in mind that this ray of the light it also has a wave characteristics, and then wave characteristics can be shown as a series of parallel lines. When you see a drawing like that, it means that wave fronts are approaching to the surface and being reflected with the angle of reflection. Now, if you have a diffused reflection, that means the reflection is in many different directions. Here, the direction of the reflection as from the smooth is very well defined, okay, with these angles. But in the case that you have a rough surface, reflection, it can actually reflect this way or that way or that way. And if you have series of these light rays, you get a diffused reflection in many different angles. That's shown with these two pictures here. And the reason this happens because roughness is a lot greater than the wavelength of these incoming lights, and therefore each ray of light can reflect in a different direction. As far as the color of the object, it is the color, the light frequency that is reflected from that object, because objects can absorb part of the frequency of the, say, white light. If they absorb that part, you don't see that colors. But objects can reflect a particular frequency from the surface of the object. For example, an apple, when you shine a white light on, the red portion of this white light gets reflected back dominantly to your eyes, and that's what you see the apple being red. Whereas other colors or other frequencies basically gets absorbed by the apple. The red frequency that is hitting the atoms on the surface of the red apple excites the electrons to a higher orbital, and then those electrons, they want to come back to the original state and emit the same frequency, which is the red. So that is the process of seeing objects with different color. Now, laws of reflections are very simple. The angle of incidence is equal to angle of reflection. Let's see if this video animation would be useful here. So let's...
of double landscape in the depth of a lake. In this video, we will study the reflection of light. First, we will distinguish between two phenomena that light undergoes, scattering and reflection. Light is scattered when it falls on leaves and reflected when it falls on water surface. A microscopic view of the surface of leaf and the surface of water reveals the reason behind this difference. When light falls on a plain and polished surface, it is sent back in a definite direction. It is the phenomenon of regular reflection of light. Note that when all the rays falling on the smooth surface are parallel, the reflected rays are parallel as well. When light falls on a rough surface, it is sent back in all directions. It is the phenomenon of scattering of light, also known as diffuse of light. Note that even when all the rays falling on the surface are parallel, the reflected rays are not parallel. This is very nice, for it allows us to see the leaf from any direction or position. When light reflects, it doesn't reflect randomly, it obeys a law, the law of reflection of light. Direct a beam of light to a mirror. A light ray from this beam falls on the surface of the mirror. The mirror, which is a polished surface, reflects the light ray. We want to draw a schematic diagram of this situation. The symbolic representation of the mirror is shown. The ray that falls on the mirror from the source S is called the incident ray. The point of intersection between the incident ray and the plane mirror is called the point of incidence I, so the incident ray is SI. The reflected ray is sent back by the mirror. It is called IR. Note that SI is directed towards the mirror and IR is directed away from the mirror. From the point of incidence, draw the line IN, which is normal or perpendicular to the reflecting surface. We usually draw the normal line dotted because it is an imaginary line drawn for practical reasons. The angle of incidence I is the angle that the incident ray forms with the normal at I. The angle of reflection R is the angle that the reflected ray forms with the normal at I.
Okay, I think you can watch the rest of this on your own. It's things that we already talked about and discovered in the wave. So here now they're talking about the light in particular. Now you may want to buy a mirror, and you wonder what size mirror you can buy. When you're in front of it, you can see your total height. Well, obviously, if you have the total length of your height, you can see everything, but you don't have to spend that much money, so you can actually get away with half of your height. The way this works is that if you have a mirror that is half of your height put on the wall at the height of your head, when you look at the mirror, the top of your head, the light from there is reflected to the mirror and reflects back with the same angle. That tells you that at this point you can see top of your head. The light from your toes, your shoes, it hits the mirror and reflects with the same angle back to your eyes. You are able actually to see your shoes as well. So let's ask this question. The law of reflection applies to, we already talked about this, applies to both light and sound and every other type of waves. Light reflecting from smooth surface undergoes a change in, what does it change here? Anything changes when it reflects from the smooth? None of these, not frequency, not speed, not a wavelength. They all stay the same because that's exactly what you see. Now, another phenomenon which we already mentioned when we talked about waves is refraction or bending. And that happens when you go from one media to another. Now, in this case, the ray of the light, as you can see, enter from air to glass. Because of the change of its speed, it bends or refracts. And of course, depending on the material and what we already talked about, index of refraction of material, the bend can be towards the normal or away from normal. We show the ray here, we show the kind of wave aspect of it as well. You can see that the wavelength is larger, but when light enters from air to glass, you have a shorter wavelength. And if you recall, velocity or speed of the was equal to the wavelength times the frequency. So the frequency stays the same. So if the wavelength is shorter, the speed will be changing. And we already talked about why that happens. Speed of light is slower going into water, from air to water. And the reverse is true also. Speed would be faster if your light goes from the water to air. So when that happens, the bending is going to be away from the normal. The law that governs this is Snell's law here, if you remember. In air, so index of refraction of air times sine of theta 1, in this case, is equal to index of refraction of water times sine of theta 2. So theta 2 called angle of refraction, as opposed to the angle of reflection when this would reflect. And of course, we talked about index of refraction earlier, and that has to do with ratio of the speed of light in the vacuum over the speed of light in the media. As you know, that if the n is larger, that means light going slower in that media or bends more. So here's some index of refraction of different material. Vacuum index of refraction is 1 because V is equal to C. And then as you go to water, you have 1.3, and glass is 1.5, and diamond is 2.4. So as density of these material increases, the index of refraction is increased as well. All right, refracted light that bends away from the normal is a light that sped up. Let's find out what is the speed of light in water for n, which we just said is 1.33, and we know the speed of light, which is 3 × 10⁸ meters per second. Use this relationship we just learned, and that's what we get. All right, one important aspect of this refraction is when the light goes from the higher index of refraction to a lower index of refraction. Now for that, I need to show you this animation. In this case, it's just the previous case. So we have air here on top and we have water on the bottom. N of water is 1.33 and N of air is 1. As we just talked about refraction, you can see how there's rays bending in the water, and there is a little bit of a reflection from the surface of water, so you see some of that going up, and then this is the refraction part. So if I show a wave aspect of this, that's what happens. Let's reverse the situation. Let's say that the top is some glass, for example, and the bottom is air. And let's see what happens here. As I increase the angle of incident, I'm inside the glass right now, and the source is inside the glass. When the light gets out, it's going to have a larger angle of refraction. Now, as I continue, increase the angle of incident, look what happens to the refracted ray. At some point, no more refraction. So in other words, all the rays reflected inside. As soon as my angle of refraction becomes 90 degrees, that means this angle, okay? Everything would be reflected back inside that medium. No more rays emerges from the glass to the air. So this is called the critical angle. And this is called total internal reflection. If you look light source in the water here, you see that this point refracts out, but as soon as this angle increased to a critical angle, which the refraction is at 90, increase of angle, all the rays would reflect back inside. And that's a very interesting and important phenomenon. It has many applications. One application is fiber optics. Now, fiber optics is kind of a plastic in the form of a cylinder that is flexible. Now, the index of refraction of this fiber optics is designed such that when the light ray hits the first surface here, it's greater than critical angle. So all the ray actually stays inside. When it hits the other surface, all the ray reflects it inside. So we have a total internal reflection. And this process continues, and as a result, all the light that gets into one side of this fiber optic comes out from the other side without a loss. And that's very important, because now you can send information from one side out from the other side without any loss. This has many applications. It has applications in communication, it has applications in medical surgeries, and so on. If you look at non-invasive surgeries, they basically have probes and they have fiber optics that they insert into where they want to operate, and they illuminate that area, and then there is another fiber optics that takes the image and brings it back and puts it on the screen. Surgeon actually with the other probe can see what's happening there and do the surgery. And then in endoscopy, in colonoscopy, to monitor what's happening in your stomach and so on. It's also in telecommunication. You have fiber optics that are miles and miles laid under the water from one location to another, and you can easily, very quickly send a signal through the light sources and capture the signal on the other side and the information through this fiber optics. In the industry, has a lot of application places that is not easily accessible. You can send a tiny little fiber optics and capture the image or things that happens in those areas. Now, when the light waves interact with each other, obviously they interfere. We talked about this extensively when we talked about the interference in the wave chapter. You have constructive interference and you have destructive interference. Obviously, this was the double slit experiment, which proved that the light behaves like a wave. Shining a light from single frequency from a source, having two opening slits, frequencies of the same light emerges from these, and they propagate throughout the space, and you will see a pattern of interference between the lights that are coming from this opening and the light coming from that opening, and they combine and superimpose on top of each other, and in certain regions they cancel each other, in certain regions they amplify to get brighter light. So you get a strips of bright and dark pattern as a result of the interference. We can show you a demo here. If I run this, there are two sources of light. The wave fronts are superimposed on top of each other. They actually form, as you can see here, a bright strip. And then the dark is when they actually cancel each other. And that has to do with a distance, an angle from one source to that particular position. And there are relationships between them, which we talked about earlier in the wave chapter. Another phenomenon that happens with light is the polarization. Now remember, we said light consists of electric and a magnetic field. These electric magnetic fields are actually, if I do this in different color, makes more sense, in all different orientation. When you have an unpolarized light, you have many electric fields that are in all direction. At the same time, you have magnetic fields at all direction. So that representation of unpolarized electromagnetic radiation or light that is propagating. We assign the direction of electric field as the direction of polarization. So if somehow you can eliminate all these electric fields on a different direction and keep one in one direction, then you have a polarized light. And that can be done by means of polarizer. Analogy to this is when you have a rope and you basically oscillate the rope up and down, and you have these fences that have opening. If you start oscillating this rope, and this rope can freely go up and down, the wave propagates through these openings up and down, and then the other one as well. Wave actually passes through. So this, you can say that this wave is polarized up and down. Now, if you turn this other fence perpendicular, the propagation stops here because the wave cannot oscillate up and down anymore. But of course, if you turn it halfway, still a little bit of that wave can propagate. The same thing happens in case of light. The electric field of the light or electromagnetic radiation it's unpolarized, usually from the sun, from different light sources. What you want is sometimes to polarize this. And we know the electromagnetic wave is a transverse wave. The propagation is perpendicular to the direction of oscillation. So we learned about that before. And therefore now we can have what we call a polarizer to eliminate all the other electric field in all the direction and keep it in the direction that we like. This polarizer letting all the electric field of A pass through, a little bit of a B pass through, and a little bit of a C pass through, but nothing of the D passes through here. And now if you put a second polarizer perpendicular to this, then it stops everything. Let me see if I have an animation for this. Yes, I do. So there you go. We have a light source, unpolarized. We polarize it with one polarizer here. Electric field goes up and down. And the next slit or polarizer is still same direction. So we still get this thing going through it. And the second one and the third one, they're all up and down polarizer. So the light can go through. Now, If I change this and rotate it 90 degrees, nothing goes through. But if I just turn it in some angle in between, then some of that electric field can go through. Here I block everything. All right, we already talked about this, and here is another example. You have two polarizer vertically up and down, and you can see everything coming through. You turn one of these 90 degrees and no light comes through, and you insert one that is half in between angle, and then some light comes through. Polarization occurs for waves that are only transverse, because longitudinal is the oscillation is in the same direction of the propagation. We use polarized eyeglasses. We want to avoid the light that is coming from the reflection of the objects and the side views, because what we want to have a nice and good clear view of the front while we're driving, for example, and avoid the reflections from other objects. When the sunlight hits, the surface or other cars, and today cars are shiny, and you notice that a lot of light reflect strongly back into your eyes. It's good to have these polarizer glasses which discriminate all the other glares that are horizontally coming, and only let polarized light vertically to come to your eyes, which is the front of you, that's where you want to concentrate while you're driving. Another phenomenon with light is dispersion. And dispersion happens when light enters from one media to another, and the other media light goes slower. We know if you have a white light consists of all these other frequencies from red to violet. What happens, each frequency refract or bend differently because of the relationship that we just talked about. Remember, also the speed depends on the index of refraction, right? C over N, which is the index of refraction of this material. In this case, is a prism, glass prism, for example. White light, when it enters, each component of that white light with a different frequency diffracts at a different angle. Turns out that blue light, which has a higher frequency, it bends more than the red. So that causes the white light to actually separate, and that's why we see the colors of rainbow emerging from the other side of the prism. Speed of light also depends on the index of refraction. Now we have these two equations. Just combine the two. So lambda times f should be equal to c over n. So from there, if you look at the index of refraction of the certain material, you can rewrite this equation as c over lambda times f. That means what? Index of refraction is related inversely to the frequency and wavelength. That's where we have the dispersion phenomena happening, and separation of the different frequencies happens because they move at the different speed inside that media. Shorter wavelength or blue is refracted, bended more. Shorter wavelength means higher frequency, and then the longer wavelength red is bended or refracted less. And one of the applications that we have been talking about in this case is when you have a spectrometer, and as a result of light going through a prism, you can separate the different colors. If that light is from a pure element, burning of one element or heating up an element like helium or sodium, then you will get these very, very well defined lines that are unique to that element and their identifier of that element. Question is, when white light passes through a prism, green light is bent more than which one of these? It cannot be more than blue or violet because those are the ones that bend much more, so it must be red. And another application is when you have a diamond or diamond cutters try to cut the diamond in certain angles so that when the light enters, first of all, it reflects multiple times inside because of the angle and total internal reflection that we just talked. At some point, it can disperse. And that's why in certain angle, you can see the rainbow color on the surface of the diamond as you rotate the diamond in front of a light source. The rainbow is another phenomenon that sunlight hits the droplets of the rain. And when those rain drops are in a certain angle with respect to the sunlight, suppose we have the raindrops here coming down and you're standing here and the sun hits the combination of total internal reflection and refraction and the dispersion causes that you can see the rainbow color from that. And the way it works is the white light enters, let's say, one drop of rain, which is water, right? So air to water. The red refracts less than a blue. Dispersion happens here. When it hits to the other side at certain angle, if this angle is around 42 degree, then you have total internal reflection. Now, one phenomena is refraction here, one phenomena is total internal reflection here, and then obviously dispersion happens. And then here, when the light gets out because there's less than critical angle at this point, and then you see the rainbow color coming out. And now you have many, many droplets, so that's what you see, a nice continuous rainbow. Let's now just quickly go over some optical devices. Important optical devices, lens. Lenses basically come in two different types, converging or diverging. Converging is when all the rays of light that enter this lens converges to one focal point. All the rays that enters this basically converge to a point here, and that point is called the focal point. Diverging lens, all the lights that comes in, they diverge away. However, if you continue the direction of all the lights that diverge, you end up with the point here on this side, and that's called the focal point of the diverging lens. Okay, converging lens, we also call it convex, or diverging lens, concave, caved in. Okay, converging lens is a kind of a fat in the middle, and diverging lens is skinny in the middle. Now, there may be different shapes of these. Overall, you see that all of the converging ones are thicker in the middle, and all the diverging one, no matter how you make it, must be thinner in the middle. How do we find image? Well, it's very simple. Suppose we are looking at a converging lens. We know the converging lens has two focal points on either side, and then there is this axis, which is called the principal axis, that goes through the center. If you have an object here, with two rays, you should be able to find the image of this object. So this object, O, you draw one ray parallel to the axis. Obviously, when it enters the lens has a higher index of refraction, remember? So it's going to bend and is going to pass through the focal point on the other side. The next ray is when you get the ray coming from the top of this object, go straight through the center of the lens. So this way is not going to bend, so because it's going through the center, and continue going out. When these two intersect, you have the image of that object. So image is inverted, and this is called a real image. Now suppose you have an object, let me see if I can do it on the same thing, object that is inside the focal point. You still do the same thing. You have a parallel line, and then that parallel line is going to go like that. And then you have one that goes through the center. But notice, these two rays are actually diverging. They're not going to cross, so you're not going to get an image on this side. However, if you continue the direction of this, let me do it in the same color, that way, and the direction of this that way, then you get yourself an image, eye here. So this is object and that's the image on the same side, and it's upright. And that kind of image is called virtual image. Now the difference is that the real image, you can project it on a screen. So you can actually see that image on a screen. However, the virtual image, you cannot see it on a screen. You can watch it from, if your eyes is on this side, you can see that object magnified, and that's what you use the magnifying glass. Now you may have a diverging lens. Let's look at that. Diverging lens, 2 focal points. And the same situation, we can apply the same rules. I'm going to go parallel to this, and I know this is going to diverge out, but it's going to diverge out that ray. If I continue it backwards, it goes through this focal point here. The other one is I go from the tip of this object to the center, and that thing is going to continue go diverge that way. Those rays are diverging. However, they intersect here at this point, which I can have an image here. I'm sorry, this is the object and this is the image. And that image is virtual, and you cannot project it on the screen, but you can actually see it. Here's the schematics of what I did here. Let me see if I have, yes, I do have an animation for this. Here is the converging lens, and here's my object, and here they have 3 rays. You can use 2 rays, should be sufficient, but 3 rays fine. So if I move this object, you can see the image, what happens if I lower the size of the object. Now if I move the object inside the focal point, as you see the image now, it's on this side and it's virtual, whereas in this case image was real. So you can use this animation to look at different scenarios. All right, okay, there you go. Now I have a diverging lens, and this is my object, and you see the image right there. So you can play with this animation on your own to get some more practice. So real image is an image that can be displayed on a screen, projector. When you go to a movie, that's real image, and it's inverted. When they do a projection, they actually run the movie upside down so that you can see the upright image. The virtual image is that you cannot project it on any screen. As a result, you can see it, but you cannot display it on any screen. And here are some examples of images. Eye is the very important optical instrument. It has a converging lens, convex lens, which is controlled by some muscles. The lens is not fixed. Focal point of a lens can change. It can get thicker or thinner, and then the focal point can adjust, because the objects that we see could be anywhere, right? So we want to be able to focus on all of that. Right away, these muscles cause the lens to adjust so that all the images are fallen on the retina on the back of the eye. And the nerves here interpret that light intensity and the color and send those through the optical nerve to our brain, and brain interprets that. Of course, part of this light bending happens in the cornea, in front of that lens. Now, the optical nerves back in the retina, they have different types. We have rods, and the other type that we call it cone. This is an electron microscope image of the rods and cones. Now, rods are responsible for detecting movement, and they're also sensitive to low intensity light. And they're on the peripheral of retina here, as opposed to cones that are sensitive to the frequency of the light, and they can recognize different colors. So if somebody is colorblind, their cones don't function well. Now, you may have issues with the lens has to be adjusted by the muscles, and that can cause trouble in terms of focusing and seeing things clearly. Light that comes from a distance focuses on the back, on the retina here, when the nerves are, and the vision is clear. And if the object is close, then the adjustment happens with the lens, so you can see the lens now thicker, so the focal point is adjusted and the image is clearly. If you're nearsight and you don't focus the distance objects well, then the image falls short of hitting the nerves on back here, so you don't see the clear image. What you need is a converging lens so that it can push the image back a little bit further to retina so you can actually see the image. And if you are far-sighted, that means if you have an object nearby, it focuses behind your optical nerves and you don't see clearly. So you need a converging lens to focus that on the right place so that you can see that clearly. So nearsightedness is called myopia and farsighted hyperopia. The near sight of your eye is the closest distance that you can focus with the naked eye. Usually for children, it's about 10 centimeter. As you grow older, that near sight goes further and further. It can go as high as 25 centimeter or more. And that's why you need the reading glasses. And then obviously, as we mentioned earlier, the eye can play tricks on you. As you can see, because of the illusion, you cannot detect the black dots here, but they seem to be there. But as you try to focus on it, they're gone. And then images can look different. Here you have an old lady with a huge nose. Here, if you move your head in and out, looking at the center dot, you see these circles are moving back and forth, whereas they're not, they're stationary. And here also, if you move your head, you can see these things are moving because of the way the eye plays tricks on you. Now let's say that we start moving closer and closer to the speed of light. What happens? Remember, we talked about electromagnetic radiation, and light was part of it. And we know that it moves at constant speed of 3×10⁸ meter per second. What happens if you move at that speed? Does that mean the light going to be at rest? And this was a puzzling thing that Einstein, had thought about it for a long time before he came up with his special relativity. On the other hand, we knew the Maxwell equations, which tell us that kind of thing is not possible. Electromagnetic waves are moving at the speed of light, and we can never experimentally achieve that kind of a speed. So Einstein came out with the theory of relativity and noticed that if you move at faster and faster speed, the concept of the distance and time will not be the same as you would know at ordinary speed. So it would affect the concept of distance and concept of time. He had a lot of thought process experiment that what would happen if an observer is moving with respect to one frame of reference and another frame of reference, and if they start moving faster and faster, what would happen? So he postulated his theory, but before we do that, let's review a definition. The definition that we use here is inertial reference frame. We talked about this earlier. Inertial reference frame is the frame that it's either at rest or is moving with a constant speed. So there's no acceleration involved there. And when that happens, all the laws of Newtonian mechanics holds perfectly true with no problem. It's like in an airplane is cruising at the constant speed of, say, 600, 700 miles per hour, and you're at the end of the airplane and your body is on front of it, and you try to throw a ball at him, and he can actually catch that ball. Your projectile motion works just as well if you were on the ground. So that's inertial reference frame. However, when the airplane is taking off, which is accelerating, right, or landing, which is decelerating, you cannot do that, because the ball that you throw is not going to get where you intended. Those laws don't hold anymore. So that we call it non-inertial reference frame. It's the frame that is accelerating, either speeding up or slowing down or turning. Remember that? We talked about that. Special relativity had two principles put forward by Einstein. And one is that consistency law principle. Laws of physics would work the same for all inertial reference frames. And the other one was the consistent of a speed principle, which is speed of light in vacuum is a constant and doesn't matter where it comes from, what is the source is independent, it's just a constant, all right? And light moves at constant speed relative to everything else. So those were the two principles. Now, then you say, wait a minute now, speed is equal to distance over time. What would happen to the concept of distance and time when you go faster and faster and faster, close to the speed of light? And that was where the concept of length and time and mass would not be the same. If you have an observer that is watching length, something that is moving at near speed of light, at the relativistic speed we call it, then that length is going to be shorter for that observer. So the stationary observer watching something that is moving at the speed of light is going to see that being shorter. By the same token, that observer will see a clock runs slower at the relativistic speed. And the same thing for the mass. If something is moving at the near speed of light, its mass or inertia increases, because whatever that is causing this thing to move faster and faster, the energy that is applied for it to move faster and faster, it converted to increase its inertia. So in inertia is going to grow larger and larger to infinite. At the relativistic speed, v, that is close to speed of light, the equations of classical mechanics, which remember E was mc squared by Einstein, and then momentum was mv, doesn't hold anymore. You have to include this factor here, 1 minus v squared over c squared, and divide this quantity by square root of that amount. So this is basically what happens when you're dealing with relativistic speed. Let me show this animation here, which is very interesting. It's about 7 minutes, but it's worth watching it.
Hi. So you want a simple guide to the theory of relativity? Great. You've come to the right place. Part 1. Classical relativity. Let's start with some absolutes that we need to accept. 1. There is no such thing as absolute motion or absolute rest. Objects move relative to each other. For example, look at the truck with two kids playing catch. The truck is moving at a constant speed of 50 miles per hour, but as the kids are also moving with it at 50 miles per hour, they could easily think that they are standing still. When the children throw the ball at 10 miles per hour, they observe that the ball they have thrown is moving at 10 miles per hour. But their little brother, who is not on the truck and is standing still, has observed that the ball has moved at 60 miles per hour. He has added both the speed of the truck and the speed of the ball together. But is the little brother really standing still? No. The Earth is constantly in motion, the Sun is constantly in motion, and the galaxy is constantly in motion. Therefore, nothing is ever at absolute rest or absolute motion. Things just move relative to each other. This is classical relativity. Part 2. Special theory of relativity, time dilation. The second thing we need to accept is that the speed of light is the same for all observers. So, let's imagine a beam of light being reflected between two mirrors. Let's replicate this setup so we have another beam of light being reflected between another set of mirrors, but this time the mirrors are moving close to the speed of light. We can see in the moving set of mirrors that the beam of light is moving a greater distance. Now, let's put a couple of people into this scenario. Meet Alex. He sits inside the moving set of mirrors, and Bill sits inside the stationary set of mirrors. The speed of light must be the same for both Alex and Bill, and their light beams must hit the bottom mirror after the same amount of time has passed. But, as Alex's light beam is covering a longer distance, how is that possible? Well, the only way for that to work is if time for Alex slows down. Look at the clock hand. Notice how Alex's clock hand is moving much more slowly compared to Bill's. Time for Alex has slowed, which allows his light beam to travel a greater distance. Look at it this way. Speed equals distance divided by time. As Alex's distance is more, the value of his time must be more. Or rather, Alex's 1 minute actually turns out to be longer than Bill's 1 minute when you compare the two. Time has slowed down for Alex. This is called time dilation. This is quite a hard concept to grasp because it seems to go against what we experience on a practical level. But to understand the theory of relativity, you must stop thinking of time as a fixed unit for everyone. Time is relative. Confused? Don't worry if you don't grasp all of this immediately. Remember, it was the most brilliant scientist of the 20th century who put forward this theory, so feel free to rewatch this part of the video as many times as you need. Part 3. Special Theory of Relativity. Length Contraction. In the previous section, we spoke about how the speed of light remains the same for Alex and Bill because while the distance Alex's light beam travels is more, his time has dilated. However, distance and time don't increase by the exact same amount. In fact, time doesn't actually dilate enough to account for the speed to remain the same for both boys. Something else happens. Length contraction. When objects are moving close to the speed of light, not only does time slow down, but the object itself contracts. This is called length contraction. So in this scenario, Alex and his mirrors are actually smaller than we thought, and therefore the distance the light beam has to travel is actually smaller than we thought also. In conclusion, time dilation and length contraction work together to ensure that the speed of light remains the same for both Alex and Bill. Einstein preferred to think of space and time not as two separate things, but one entity. He called it space-time. Part 4. Time travel. Time slows down for objects travelling close to the speed of light, and time stops altogether for objects travelling at the speed of light. It then follows that time must go backwards if objects travel faster than the speed of light. So far, it has been seen that no object can travel at the speed of light. On approaching the speed of light, objects start to increase in mass rather than speed, and it would take an infinite amount of energy for an object to achieve the speed of light. This is why we cannot travel back in time. We simply have not been able to reach a greater speed than the speed of light. Part 5. General Theory of Relativity.
Okay, so let's hold on to this. We'll come back. Now, there are other very, very important and nice videos, demonstrations here. One is about how the GPS actually works and why we have to make adjustment in the clocks on the satellite versus the clocks on the Earth, because the satellites are moving way up there above the Earth, as well as they move fast around the Earth. We have to make adjustment because of this phenomena of the time dilation. So these are very nice videos that I want you guys to watch it on your own time. And then we move on to general theory of relativity. And the essence of general theory of relativity is that the gravitational field, the attraction, gravitation that we know, that we talked about a lot at the beginning of the course, and acceleration are basically of the same nature and same thing. In other words, if you are being pulled down by gravity of g 9.8 meter per second squared on the Earth, you would feel the same thing if you're way out in the space and in some shuttle accelerate at 9.8 meter per second. You won't feel any difference. The gravitational interaction in the masses are as a result of the acceleration that is happening, and we feel that as acceleration. Now, there's this video which it's very interesting and shows the concept of gravity, and gravity in solar system works with this demonstration, which I want you guys to watch it, because in the interest of the time, I let you guys watch it on your own, and then we have some questions for you about it. So make sure you watch that video. It's a very, very interesting video. One application of this special relativity time dilation has to do with the satellite. So experimentally, we actually know that this is happening, because when we have these satellites out there that are giving us direction, GPS direction on your car, on your cell phone, what have you, within the distance 1 foot. The military ones are even within inches. What happens there must be a clock in the satellite. The satellites transmit signals onto the Earth and then receive the signals back. There is a clock that is working on those satellites. And of course, we have a clock on the Earth. Now, it happens that because these satellites are way up there, about 20,000 kilometers above the Earth, gravity due to the Earth is a little bit different. That's one thing. The other thing is that these are moving at very high velocity, at 4 kilometers per second, 4,000 meters in 1 second. Now, they're not too high compared to the speed of light, but it still has an impact, because there is a difference between the clocks that are running on the Earth and the clocks that are running there. And that difference is enough to cause error, huge error, because if those clocks on the satellites are not adjusted, even though the amount is very small, 3 nanosecond, 3 10 to the minus 9 second, and these are atomic clocks, so they're very, very accurate. If we don't adjust for that, the distance that satellite would tell us on your GPS on the car could be off hundreds of feet, and that's not good. We do have to make that adjustment because of the motion of high velocity of these GPS satellites, which has to do with the special relativity, and also the location with respect to the Earth, which is about 20,000 kilometers above, and the difference between the gravitational force on the surface and the gravitational force up there. We have to make this kind of adjustment in order for it to be accurate. Okay, again, I have more videos here, so let's just continue watching this one.
Einstein realized that the special theory of relativity, which we explained previously, only worked for circumstances when things moved at constant speeds through the universe. What about when objects sped up? What about the effect of gravity? And come to think of it, what is gravitational pull after all? Einstein theorized that objects warped space-time around it, causing it to become curved, and as a result, objects experienced gravitational attraction to each other. This warping of space-time explains how objects behave as they move through space. This is the general theory of relativity. Part 6. How do we know it's true?
Now, remember we talked about inertial reference frame, and we talked about non-inertial reference frame. So now, if we have these accelerations, Therefore, we're talking about non-inertial reference frame.
Part 6. How do we know it's true? How do we know that the theory of relativity is true? Well, countless experiments have been carried out, and Einstein's equations hold true. Modern GPS uses Einstein's theory of relativity to pinpoint our locations with impressive accuracy. In 1971, an experiment was conducted with 4 super-accurate atomic clocks, which were set to the exact same time as a reference clock. The clocks were placed aboard commercial flights, and the planes flew twice around the world, first eastward and then westward. When the clocks returned and were compared to the reference clock, the clocks were no longer all synchronized, and the differences were consistent with the predictions of special and general relativity. So, that concludes our explanation of the theory of relativity. Bear in mind this is a very simplified explanation, but it should give you a basic understanding of the core ideas so you can study further on your own.
All right, great. And also I have these other videos here that are very, very interesting, and I want you guys to watch those as well. Now we kind of come to the end of coverage about the physics part of this course. You know, we touch upon a lot of these phenomena that happens in classical physics, and a little bit on relativity and a little bit on quantum physics. But if you're interested to see what else is going on, definitely watch this video on YouTube. It's a nice coverage about the landscape of physics. I would recommend that to you guys. Okay, we are at the end of this chapter, and have a nice day, and I will see you next time.